Hello, everyone. Welcome to our YouTube channel. My name is Hans-Jürgen Schönig. Thank you for joining up for this session. So basically, many support customers are asking us, why does vacuum not shrink my table? So let's dive in and let's figure out. Before we get started, I want to tell you something about my company. My name is Hans-Jürgen Schönig. I'm a senior database consultant, and I'm the CEO of CYBERTEC. We've been doing professional Postgres since 1999, and we operate internationally, providing Postgres support and consultancy. So if you need anything, just get in touch with us. So, vacuum, reclaiming space. As I stated before, this is one of the most common issues people are asking us on the customer side. So I thought it's worth creating a little bit of insight into this important topic. So when we get started, the first thing you have to know is what's the basic layout of a Postgres table. And basically, a Postgres table is a collection of 8 kilobyte pages. And when we're talking about the standard vacuum, we have to keep in mind that vacuum is basically a block level operation, right? So you will figure out a bit later what I mean by that. So why do we need vacuum in the first place? So what's the whole purpose of this thing? And the reason is, as you might know, Postgres allows for quite a lot of concurrency. So if you have a table, there might be many users operating on this table at the same time. So in my example here, the person on the left-hand side might run a transaction. It's going to update the value. Let's say update number, set value equals 4, where value equals 1. And some other guy might do some other transaction at the same time. At the end of the day, Postgres has to make sure that every transaction sees exactly the data it's supposed to see. In my example here, the right transaction is not going to see anything because the value we want to change has already been changed on the other side. So that's what I mean by if there's concurrency going on, the database has to ensure at any given time that the right transaction is going to see the right piece of data every time. What it means is that my update statement has to duplicate the row, right? So update has to duplicate the row to make sure that every transaction is going to see the right data. So update is not going to overwrite the data. It's going to duplicate the row to make sure that we can roll back and to make sure that every transaction is going to see what it's supposed to see. And the problem that is naturally arising from this kind of behavior is generally known as table bloat. So what does it mean? So what I've done here is I've created a small table, create table A. It contains one integer value. And what I've done here is I've turned all the vacuum off. You should not do that in production. I've just done this here to make the example work the way it should be, just to make sure that there are no automatic side effects caused by timing or so. So I've created a table, one entry. And then I've loaded a million rows into this table. And what we see here is that the size of the table is something like 35 megabytes, right? So that's the boring part. But let's move on to the real example. If we update this table, so if we update every row, what we see here is that the size of the table has basically doubled. So as I've told you before, update has to copy all the rows, okay? And this actually means that the copy of the row has to go to this table, okay? So therefore, the size is going to change. The main question now is, how can we handle this space in a way? How can we reuse it? And that's exactly the purpose of vacuum, right? So let's see. If we run vacuum, what it's going to say is vacuum of table A, right? So vacuuming public.a, And then it says removed 100,000 rows, 1 million rows. 1 million rows are removable and 1 million rows are not removable. And if we check the size of the table again, what we see here is that it's still 69 megabytes. So that's the thing many people don't understand, or what they complain about is that they keep vacuuming, but the table doesn't shrink again. It's still going to be a large table and performance goes down. So the question is, why is that? And the answer is the way vacuum is going to reallocate the space, right? So in order to see what's going on there, we can create an extension. So we can load an extension into the database, which is called PGStat-tuple. When we run select star from PGStat-tuple on this table, we can basically look inside the table and see how it's organized. In my case, what we see here is 70 megabytes of data, 1 million rows. And that means basically that 28 megabytes were allocated for the data, which is 38%. But remember, we inserted some data, we updated, and we vacuumed. So what happened is that if we update a couple of rows, we got two versions, the old one and the new one. And in my case, the old one is already dead because nobody can see the old version anymore. So what vacuum did was it basically scanned the table, it checked for those dead rows, and it converted those dead rows to free space. So if we run insert or update again, instead of growing the table, Postgres is going to take the space that is already there and use it for future operations. So vacuum does not shrink the table by making it smaller. It's simply going to check what there is, and then space can be reallocated in a way that you can use it for future transactions. Okay, so that's super important. The point is, vacuum operates on a per block basis. So vacuum is going to touch first block, second block, third block, etc., and it's going to fix the block. It's not going to move rows from one block to the other, right? So standard vacuum is not going to do that. So it could be that full blocks are interleaved with empty blocks, etc. Right? But the size of the table usually doesn't change. That's very important observation because many people assume that the table is actually going to shrink, which is of course not the case. So let's think about some implications here. I said vacuum is allowed to reclaim dead rows. Okay, so the main question is, when is a row considered to be dead? So when can we kill it? So let's look at an example. Let's take a look at the right-hand side of this slide. We start a transaction and we delete a row. This deletion is not allowed to physically remove the row. It's only marked as removed for your transaction, but it's still there. Because if you want to roll back, you still need this row to be there, okay? So we cannot remove the row on delete. But even if we commit, we are still not allowed to physically delete this row. And the reason is that there might be a concurrent transaction, so a transaction running at the same time, which still needs this row. It's still visible. So in our case, there's a long select statement in connection number one, and it's still going to see the data as it was before the deletion. Okay? So what it means is that our first vacuum on this slide is not allowed to remove anything from this table because the left transaction can still see the data. So only if the left transaction commits, then can the vacuum actually go out and seek those dead rows and actually see that they are dead, okay? Because before they were technically still alive, okay? So this is super important that even if you run vacuum, it might not be able to reallocate the space because some concurrent transaction is going to see this data. So that's super important. And this is the core, the main reason why people assume that why does my table keep growing for whatever reason? I keep running vacuum, and the answer is long transactions, open snapshots, whatever. Um, so that vacuum cannot do its job. But even if it does not mean that your table is going to shrink. Okay. There is just one exception. There's actually a case where vacuum can shrink a table. And if you look at this graph, if from a certain point in the table onwards, only dead rows exist. So let's suppose you got 10 gigabytes of data, and only the first half of the table really contains visible rows. All the rest is empty because of some aborted insertion or something. Then vacuum can shrink the table. It's just not very likely that this is possible. Okay, so in the normal system, a normal OLTP system, that's not feasible at all. Okay, but it can be feasible in some warehousing, staging tables, or something like that. So in my case, if I delete a million rows just because, and if I run vacuum, then Postgres is going to figure out that from a certain point of the table onwards, there is no data anymore. Okay, so then it can truncate the table. In my case, we are very lucky because I happen to delete all the rows. So the size of the table at the end is going to be 0. But in practical terms, this does not happen too often. So vacuum can shrink a table, but it's not the regular thing you would see on your system. If there's a single row towards the ends of the data file, then it's not going to happen again. Okay. So thank you for your attention. I hope you like this first video in the series. I highly invite you to follow us on Twitter, like us on Facebook, and ring that bell on YouTube to make sure that you get all the notifications about our brand new videos, which we are trying to put out on a regular basis from now on. So I hope you like the show, and please leave your comments in the feedback section and get back to us so that we can produce more content and to make sure that we are producing exactly what you guys want to see. So thank you from my side, and happy YouTubing.